Welcome to the mini lecture series on the Professor's DuBois channel. This is Professor Corey, and today I'm going to talk about factors that affect gas solubility. In our previous lecture, we talked about predicting solubility, and we had two components we had to consider. We had to consider the enthalpy and the entropy of the system. When we look at the gas solubility, we're also going to have to consider these. So if we look at enthalpy first, remember we said we could predict enthalpy based on the amount of energy from the bonds breaking the bonds, and then we could subtract the energy released from the bonds forming. Well, the gas state really doesn't have any bonds. The gas is free to move around, so there really aren't much for bonds broken. So we've got a really small amount minus some number from the intermolecular forces being formed. So we're ultimately going to have a negative delta H, which is favored. But the entropy, on the other hand, is not favored. The gas is really free to move about. And if we dissolve it or constrain it within a liquid, it doesn't have the freedom that it once had. So our entropy is not going to be favored. So another thing we need to consider is that gas solubility is the concentration of that gas at the equilibrium. If we look at our predicting solubility chart, we could say, okay, we're enthalpy favored because the bonds broken minus the bonds formed, but we're not entropy favored. So the gas in this case, will be soluble at lower temperatures. And this is true. Henry's law is a formula that we can use to calculate the solubility of a gas, or we could call this the equilibrium concentration. So we're going to have units of concentration for our solubility of the gas. The K is the Henry's law constant, and this is specific for the gas-solvent mixture and the temperature. So we don't just have one constant that applies to everything here. This is every gas solvent combo has a constant, and if the temperature changes, then the constant also changes. Our P value here is the pressure of the gas above the solution. So we can see down in the bottom image that we have this, what we will call headspace. And so there's an amount of gas up there. Now, if we had more gas up in that headspace, we'd have a higher pressure. And with a higher pressure, you can see we'd have a higher solubility or a higher concentration of the gas in the liquid. Another way to look at the solubility is to kind of write almost like a chemical reaction. And we'd said that the enthalpy of a solution for a gas is exothermic. So this was the bonds broken minus bonds formed. Well, if it's exothermic and we have a negative delta H, that means that energy is really a product of that reaction. So you can see here we just wrote gas plus liquid solvent, and we have a set of double arrows here, which is new. But we're forming a saturated solution plus energy. We're just going to write the energy in as a product because it's exothermic. Now back to those double arrows. Those double arrows mean that we have an equilibrium. So what's going on here is this reaction can run in both directions. But when it reaches an equilibrium, it'll still be moving in both directions, but in the case of going to the saturated solution, if we form some more saturated solution, then it'll run the other direction and form more gas and liquid solvent. What an equilibrium does not mean is that everything's equal on both sides. We can have an equilibrium that's primarily products, or we could have an equilibrium that's primarily reactants. In this case, that's not important. This will be important later. But for now, we just want to know where would the energy go in this reaction. So in this case, we said it's exothermic, so energy is a product. So what that means is if I change that energy, I could add heat, I could remove heat, it'll stress that equilibrium. And the equilibrium is going to try to fix it. It's going to try to go back to where it was. So if I add energy, it's going to say, geez, I've got too much energy now. I need to run in the reverse direction and make more gas and liquid solvent and use up some of this extra energy. I'm going to use some of the saturated solution in the process, and I'm going to end up with more gas and liquid solvent. Well, in the case of our let's say our carbonated beverage, if I get it hot, that's going to shift the equilibrium back toward liquid and gas separate, not good. So we want to reduce the energy or lower the temperature. If we do that to the equilibrium, if I lower the temperature, the equilibrium is going to say, geez, my energy is too low. I need to run more in the forward direction, use some of my gas and liquid solvent to produce more saturated solution and get that energy back to where it was. So these equilibriums can shift if we stress the system. So all we're looking at now is the energy component. So again, we've got gas and liquid solvent. We said it's an exothermic process, so the delta H is less than 0. It's negative. That means we can write energy as a reactant in this reaction. If we add energy, if I add heat, this equilibrium is going to say, geez, I've got too much energy. I need to run in the other direction, get that energy back down where it needs to be. That's going to shift the equilibrium to the left, making more gas and liquid, depleting some of that saturated solution. So in essence, what we're doing in this case is reducing the solubility of the gas. It's definitely worthwhile looking at this Le Chatelier principle and understanding how changes in the energy can shift our equilibrium, because this Le Chatelier and equilibrium is going to come back in further chapters. So I hope this was helpful. Stay tuned for the next mini lecture on the Professor's DuBois channel.